Hello, pre-calculus. In the last video, I left us with this example of something we didn't know how to solve. I left us off with this example where I said, look, if I have 2 to the x power equal to 13, we can't rewrite those bases and solve it. We're going to have to use some properties of logarithms to solve this. So first off, we need to remember what the definition of a logarithm is. So what we have here, when we talk about logarithms, if I have log base b of x equal to y, that is equivalent, meaning exactly the same, meaning similar to b to the y power equals x. So these two statements mean the same thing, and we're going to use them sort of interchangeably to help us solve some problems similar to this here, actually, similar to what we have here. For solving 2 to the x is equal to 13, we need another property of logs that we talked about in a previous video, where we said if I take log base b of b, that's equal to 1. I'm going to use my equivalent property here so that I can understand what this means and why my answer of log base b of the argument b is equal to 1. So the log base b of b is equal to 1 is equivalent to saying b to the first power is equal to b. And that's true. So I hope that's helpful. Let me give you another example just with some concrete numbers. If I asked you to tell me log base 2 of 2 is equal to some number, I wanted you to solve that for me. I would expect you to say, this raised to the question mark power. 2 raised to the question mark power is equal to 2. What is that question mark? It could only be 1. Could only be 1. That's our only option. Hopefully that helps a little bit. So we're going to use these two to actually solve our nice little example that we were left with before. So if I have 2 to the x is equal to 13, here's what I'm going to do. I'm going to take the log with a base of 2 of each side of the equation. And so what I'm left with here is log base 2 of 2 to the x power is equal to log base 2 of 13. And then we have a property that's going to let us actually handle this exponent here. We have a property of logarithms that says if I raise something to an exponent inside the argument, I can actually bring that exponent down here. So now I'm left with x times log base 2 of 2 is equal to log base 2 of 13. And I can say the log base 2 of 2 is equal to 1. So now I have x times 1 is equal to log base 2 of 13, which is the same thing as saying x equals log base 2 of 13. And if you plug that into your calculator, you get a gnarly long decimal, but you can round it. And it rounds to about 3.32. And that would be your final answer. You'll see this problem-solving method that I just laid out to you with a fairly simple example comes up a lot in applied problems with some really gnarly little strange-looking details. We'll do an example of that in class, and I think it'll help. I think it will help. So I'm going to remind you of the logarithm definition, and we're going to talk about how we can use that to solve some problems. So remember, we said at the top of this video, and I will say over and over again, that log base b of x is equal to y if and only if b to the y is equal to x. This phrasing, if and only if, is sort of mathematical lingo. What it means is that if our first statement is true, our second statement has to be true. And if our second statement is true, our first statement has to be true. They both depend on one another. I'm sorry, you can hear my dog barking in the background of this video, doing his best to ruin our class, as always. But you know we love him. All right. And so we're going to use this to help us solve some equations. Let's do a nice little example so you can see what I'm talking about. Let's suppose I have this equation. 2 times the ln of x plus 3 is equal to 7. Don't let this ln intimidate you. This is just a logarithm, and it's a logarithm that has e, the irrational number e, as its base. Remember that. We're going to use that fact in a second. The first thing we want to do is we just want to isolate this logarithm. We want to treat this logarithm as if it were the variable. I'm going to get it completely by itself. So I'm going to start off by subtracting 3 from each side. Then I have 2 times the natural log of x is equal to 4. Now divide each side by 2. And now I have the natural log of x is equal to 2. And here's where we're going to use our definition here. Remember, the natural log has a base of e. And so this statement, natural log of x is equal to 2, can only be true if e squared is equal to x. And this would actually be your final answer here. I would not want you to type it into a calculator or round it. This would be a perfectly acceptable answer. Remember here, e, don't be intimidated by e. E is just an irrational number. I hope that helps. Let's do another example. We'll do another example involving e, and then we'll do an example with a different base. So let's suppose I had this situation. I have 6 plus the natural log of x is equal to 10. Just like before, we want to isolate this natural log. And we want to isolate that by subtracting 6 from each side of the equation. And then I have the natural log of x is equal to 4. This can only be true if the equivalent exponential statement is true. So this is true, the ln of x is equal to 4, only when e to the 4th power is equal to x. And that actually gives us our final answer. Just translating this statement from its logarithmic form to its exponential form gives us our answer. Let's do one more example. Let's use a different base though. Let's try 2 times the log base 4 of x is equal to 1. And we're going to solve this the same way, just we're going to have a different base. So our first move is we're going to isolate this logarithm here. And I'm going to do that by dividing this equation by 2 on each side. Now I have log base 4 of x is equal to 1/2. And I'm going to use this to translate this into the exponential form. I think I mentioned in one of my videos, one of my colleagues called this the swirl. He said, because you take 4 to the 1/2 power, and that's equal to x. And so he saw it as kind of like a swirling action, and that's how he remembered it. That never worked for me, but I include it because maybe it'll work for you. If you like thinking of it as the swirl, if that's helpful to you, go ahead and comment and let me know. I'm curious. So now I have 4 to the 1/2 power is equal to x. Don't freak out by this 1/2. Remember, 4 to the 1/2 power is the equivalent to the square root of 4 is equal to x. So here x is equal to 2. And that would be your final answer. All right, so that's one way that we can solve logarithmic equations. We also have another property of logarithms that lets us to solve a slightly different, slightly more complex class of equations. This is called the one-to-one property of logarithms. And it's very similar to what we use when we solve exponential equations. because logarithms are, in a way, just exponential equations. So this is another if and only if statement. If I take a logarithm with a base of b of x, and that's equal to the logarithm with a base of b of y, then x has to equal y. So if I have these logarithms equal, x has to equal y. So what you're checking in this situation is you want to make sure your logarithms each have the same base. And then when that's true, you can set these arguments equal to one another. Let's do an example. Suppose I have the natural log of x squared equal to the natural log of 2x plus 3. So both of these logarithms have a base of e, the irrational number, which is the same. So because they both have a base of e, those are the same, it means I can set what's inside these parentheses equal to one another. So we get x squared is equal to 2x plus 3. And now we solve this little equation. So I'm noticing here though, we've been working with linear equations. I notice I have a quadratic here. So we're going to have to dust off our quadratic solving skills. So I'm going to subtract 2x from each side. X squared minus 2x is equal to 3. And then I subtract 3 from each side. X squared minus 2x minus 3 is equal to 0. You could do it all in one step if you like, but I'm teaching, so what's the rush, right? I might as well show you in 2 steps. You can solve this any method you like for solving quadratics. I'm going to choose to factor here because I happen to know that I can factor this fairly easily. But if I couldn't factor it, I could use a quadratic equation, no problem. And now here I have 2 answers. X is equal to 3 or negative 1. There is something, let's not box that answer yet. Don't get ahead of ourselves. We have to check our answers here. Because remember, I want you to recall, you can't take the log of a negative number. It doesn't exist. There's no solution. So what we have to do is we have to look at our original equation, ln of x squared equals the ln of 2x plus 3. And we have to make sure that if I plug in x is equal to 3, I don't accidentally end up with a negative number. I see if I plug in x is equal to 3, I'd get 9 and 9. That's great. And then I'm also going to check by plugging in x is equal to 1, negative 1, and make sure that I don't get a negative number there. Let's see, and now I'll check negative 1. So I'll plug it into each one of these arguments, and that'll tell me. And I'll get negative 1 squared, which is positive, so that's okay. And then 2 times negative 1 plus 3, that's negative 2 plus 3, that's 1, that's okay. So you just have to double check and make sure that your answer makes sense. If one of these values had given me a negative number inside my logarithm, I would have thrown that answer out. That would have been an incorrect solution. So it's true, we can say that x is equal to negative 1, 3. And use those beautiful curly braces. Let's do another example. Let's say the ln of x squared is equal to ln of 1. And then I can say we have the same base at this natural logarithm. So then x squared must be equal to 1. So then x is equal to negative 1 or positive 1. And I do a quick mental check, and I say those will both give me positive numbers in the argument. So that would be my final answer there. I would like you to, at this point, read through the applied example at the end of your interactive textbook. We'll talk about it in class, but I want you to take a look at it. I want you to at least get started thinking about it. But that's all I have for you about logarithms and exponential functions. I hope you're having a good day. Stay safe out there.